Welcome back to statistics. Today we're going to talk about probability and statistics. First, a definition. An experiment is any process of observation or measurement as an example of an experiment. Notice that I observe that I've just rolled a 6 and a 2 on this pair of dice. That's an experiment. The set of all possible outcomes of an experiment is called the sample space and is usually denoted by the capital letter S. As an example of a sample space, consider all possible outcomes for the roll of a die. In this case, a sample set is a set. It begins and ends with a curly brace. All possible outcomes are listed, delimited by commas. There. The sample space for all outcomes from the roll of a single die. For the roll of 2 dice, the sample space is a little more complicated. We might consider that we have a first die and a second die, and they can have different outcomes. So in this case, for 2 dice, the sample space will consist of a 1 on the first die and a 1 on the second die. A 1 on the first die and a 2 on the second die. All the way out to a 1 and a 6. We can continue on the next line. A 2 on the first die and a 1 on the second die. A 2 and a 2. A 2 and a 3. All the way out to 2 and 6. And you can see we can keep going until we have these 36 possibilities. A single element from a sample space is called a sample point, or sometimes a simple event. So example, the event of rolling a 6 is an element of the sample space that consists of possible rolls of a single die. And so 6 is a sample point. Any subset of a sample space is called an event. As an example, suppose I'm rolling a single die. One event could be I roll an even number. That's a subset of the sample space. Another event, let's call this event number 2, might be I roll an odd number. Events can take any number of different forms. One event might be I roll either a 1 or a 6. These subsets are sets, so they begin and end with a curly brace. We're now going to define certain postulates about what we mean by the word probability. First, the notation. The probability of an event E is denoted by capital P of E. We think of probability as a function. You feed in the event, it outputs a positive real number associated with that event. That number has to satisfy certain facts, certain postulates. The probability can't be negative. It can be 0. It is possible to have an event with no possibility of happening. Second, the probability of the entire sample space, which is all possible outcomes, is 1. We'll assume that something does happen when we perform the experiment. So if we're flipping a coin, we're going to assume that it's either heads or tails, and we don't get edge, the coin lying on its edge. A third postulate is that if events A and B are disjoint in the sense that they share nothing in common, the intersection of these two sets is the empty set. Then that'll affect the probability of the joint probability of A and B thrown together, A or B. A union B is often thought of as using the word or. A is either in A or in B. An intersection is the word and, A and B, something that lies in both. We get the sum of the probabilities if these events share no simple events in common. To illustrate this idea, let me show you a Venn diagram. So event A might be over here. To be disjoint, event B can have no terms in common with A. No simple events, no elements in common with the event A. They're disjoint. So the probability of getting something in either event A or in event B will be the sum of the two probabilities of these independently. The probability of getting A plus the probability of getting B. A fourth idea that's kind of embedded in what we're saying here, property 4, if you will, is that the probability of an event can't be bigger than 1. The reason being is that the probability of all possible events is 1. So any other subset of S can't give you a probability higher than 1, but it can't give you a probability lower than 0. So probabilities will always be numbers between 0 and 1. 0 means it won't happen. 1 means it definitely will happen. 1/2 means there's a 50-50 chance. 50%. If you multiply the probabilities by 100%, you get the percent chance of an event happening. Let me give you an example. Suppose that event 1 is I roll either a 1 or a 2 on a die, whereas event 2 is the chance that maybe the event that I roll a 3 on the die. So the probability of event 1 or event 2, remember this stands for or, the union symbol, will be the probability of event 1 plus the probability of event 2. Notice that the probability of getting any single number for a fair die will be 1 in 6. There are 6 possible outcomes for the roll of a fair die. The probability of rolling a 2 is 1 in 6, and so on. The probability of event 1 here will be 2 out of 6. The probability of event 2 will be 1 out of 6. So the probability of getting either a 1 or a 2 or a 3 is going to be 2/6 plus 1/6, which is 3/6 or 1/2, reducing the fraction. 3 goes into the top once, 3 goes into the bottom twice. That should make some kind of sense, because the numbers 1, 2, and 3 are half of the elements of the sample space, and each possibility is equally probable. We're going to codify this idea in the following statement. If the sample space S consists of n equally probable simple events, and event E consists of, let's say, X simple events, then the probability of event E will be the number of simple events in E divided by the total number of possibilities. So in our example of throwing a single die, suppose the event consists of 1, 2, or 3. The probability of that event will be 3, there are 3 elements, 3 simple events within this event, divided by 6, the total number of elements in the sample space, or 1/2. If you don't know whether or not the simple events are equally probable, you can still experimentally estimate the probability of an event. What you'll do is perform n experiments if event E occurs X times, then the probability of E is approximately X divided by n. The more times you perform the experiment, the better this estimate should get. Let's do a quick example. Let's suppose E is the event that I roll a 2, 4, or a 6. I'm going to perform an experiment 10 times, where I roll this die 10 times, and I see how many times I get an even and how many times I get an odd. The first roll was a 2. The second roll was a 1. The third roll was also a 1. The fourth roll was a 6. The fifth roll was a 2. The sixth roll was a 1. And then the seventh roll was a 2. And then another 2 on the 8th roll. A 3 on the 9th roll. And a 5 on the 10th roll. So for us, the probability of the event of getting an even on the roll is about, we'll just say approximately 5 out of 10, or a 50-50 chance. This won't happen in every experiment of 10 rolls, that you get exactly the expected probability for a well-balanced die. For all I know, this die is not well-balanced, so it may not give exactly a 50-50 chance of rolling even versus odd. It just so happened that in this experiment of 10 rolls, that's what we got. There's something called the law of large numbers that you need to know. And it goes like this. As the number of trials goes to infinity, the experimental estimate tends to exactly the true probability of the event. So to get a better and better approximation to the actual probability, you have to take bigger and bigger values for n. The complement of event E is denoted by E bar and defined by E bar is everything in the sample space except for the simple events in event E. In a Venn diagram, if event E is here, then the complement is everything else. As an example, suppose that event E is the event that I get an even number when I roll a fair die. Its complement is everything else. One thing to note is that E together with E bar is the entire sample space, because if it's not in E, then it has to be in E bar, the complement. And there's nothing in common to these two. So their intersection, the overlap, is empty, the empty set. Sometimes denoted by just braces with nothing in it. It follows from our postulates about probability, and 3 dots and a triangle means therefore, the probability of either of these happening will be 1, but it must also be the probability of E plus the probability of its complement. By rearranging the terms, by subtracting the probability of E from both sides of the equation, we finally come to this. The probability of the complement of an event is 1 minus the probability of the original event. This is a formula you need to know and be aware of. We will use this throughout the course. As an example, suppose our event is that we roll a 1 with our die. The complementary event is getting something else. The probability of E rolling a 1 is exactly 1 out of 6. There's only one simple event in there out of 6 possible simple events in the sample space. So the probability, them being equally probable, we will assume, is 1 out of 6. What's the probability of E bar? Well, clearly it's going to be 5 out of 6. But we can calculate it this way as well. 1 minus the probability of E, which is 1 minus 1/6. When subtracting fractions, you have to have a common denominator. So you have to multiply 1 by 6 over 6 in order to subtract the fractions. 6 minus 1 is now 5, and the 6 will remain the same. So the probability can be calculated this way as well, besides just observing there are 5 elements in the complement of E and 6 elements in the sample space. As another example, suppose I have a deck of cards with 52 cards in it, separated into 4 suits with 13 cards each. Let's call them spades, hearts, clubs, and diamonds. The probability of drawing a heart is 1 out of 4. The complementary event, the probability of drawing something that is not a heart, will be 1 minus 1/4, or 3/4. An event is unlikely if its probability is small. Now, what do we mean by a small probability? Something close to 0. We're going to establish certain conventions for this course as to what we mean by small. And so, if the probability of the event is less than or equal to about 0.05, that's about a 5% chance, or less, then the probability is small. So for this course, any probability less than 5%, less than 0.05, will be considered to be unlikely. As an example, suppose I'm drawing from my fair deck of 52 cards the ace of spades. What is the probability of drawing the ace of spades? Well, it's just one card, a simple event, out of a deck of cards consisting of 52 simple events. This is definitely less than 0.05, which is about 1 in 20. And so this will be unlikely. Let's give you some examples of some other probabilities. Let's suppose that we're having a baby, and we have a father and a mother, and the mother has blue-eyed genes. Blue eyes, blue eyes. She has 2 of these blue-eyed genes. The father has brown eyes, but he carries the blue-eyed gene. Brown eyes would be the dominant gene, so since he has one brown-eyed gene, his own eyes will be brown, but he carries the blue-eyed gene. What will the offspring have? This offspring, if he passes on the brown-eyed gene, the mother will pass on a blue-eyed gene. This offspring will be brown-eyed. Same here. But if he passes on his blue-eyed gene, and she passes on her blue-eyed gene, you can see that these children will have blue eyes. There are these 4 simple events, equally probable. So the probability that the child has brown eyes will be 2 out of 4. the probability that the child has blue eyes is also 2 out of 4. We have a 50-50 chance of the child having either brown eyes or blue eyes. Suppose, as for another example, that father and mother both have a brown-eyed gene, so they both have brown eyes. You can see then that if they both pass on the brown-eyed gene, the child will clearly have brown eyes. We can have two situations where the child has a brown-eyed gene and a blue-eyed gene, and one situation where the child has blue eyes. So the probability of blue-blue is 1 in 4. There's only a 25% chance of the child having blue eyes. The probability of brown-brown or brown-blue or blue-brown is 3 out of 4. So there's a 75% chance that the child will have brown eyes. Consider the event that I toss a coin twice. What are the possibilities? My sample space could be thought of as getting heads and then heads, heads and then tails, tails and then heads, tails and then tails. So the probability of getting 1 head and 1 tails, that occurs twice out of 4 events. There's a 50% chance of getting exactly 1 head. The probability of both heads is 1 in 4, and the probability of both tails is 1 in 4. So here I have my coin. I flip it. In my experiment, I get a heads. And if I flip the coin again, I still get heads. So I ended up with this event, this simple event from my sample space. The probability of that happening is about 25%. There's something called the fundamental counting principle. If we have 2 events, one of which has m possibilities and the other one has n possibilities, the total number of possibilities is the product, m times n. So for example, if I'm tossing 2 fair dice, there are 6 possibilities for the first die and 6 possibilities for the second die. That gives us 36 possibilities in the sample space. For a coin, it would be 2 possibilities on the first flip, heads or tails, 2 possibilities on the second flip, for a total of 4 different elements in the sample space. 4 possibilities when I flip the coin twice. So for example, if I flip a coin 6 times, how many elements are in the sample space? We'll assume they're all equally probable, but that's really not the point here. There's 2 possibilities, heads or tails, on the first flip, 2 possibilities on the second flip, 2 possibilities on the third, fourth, 5th, and 6th flips. That gives me 64 elements in the sample space. If I'm looking for the probability of 6 heads in the flip of a fair coin. That can only happen one way, all heads. That's one element in the sample space that has 64 elements. So the probability of getting 6 heads in a row is 1 out of 64. This would be an unusual event, because this is less than 0.05. There's a general addition rule. For probabilities. It's based upon the following picture. Suppose we have a Venn diagram where we have 2 events, event A and event B, and suppose they overlap. There are some events in common, some elemental events in common to these 2 events. So what is the probability of getting A or B? It can't be just the probability of A plus the probability of B, because there are events in common. If we account all of the events in event A, and then all of the events, simple events in event B, the intersection is counted twice. So we need to subtract off the probability of getting A and B, since those were double counted. As an example, suppose that we have a cancer test. And we administer this cancer test to a whole bunch of people. And there are those who do not have cancer, versus those who have cancer. There are those who test negative for cancer, so they don't test positive, and those who test positive for cancer. You see, the cancer test may not be perfect. It could make mistakes. And suppose that amongst those who do not have cancer and test negative for cancer, we have, let's say, 200 individuals in this group. Those who test negative for cancer but who actually have cancer, let's suppose there are 5 in this group. Those who test positive for cancer and yet later are found not to have cancer at all, let's suppose we have 10 in this group. And those who test positive for cancer and actually have cancer, let's suppose that there are 35 in this group. We have 35 and 5 makes 40, 50, 250 individuals altogether. So we perform the experiment 250 times, and these are the results that we end up with. Suppose we look at the 2 events. Event A is the event that you do not have cancer, and event B is the event that you test negative for cancer. How do we then determine the probability of A or B? The probability that you either do not have cancer or test negative. And according to the addition rule, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. This is an AND symbol here. Well, the probability for event A that you do not have cancer is 210 out of 250. There are 210 people who do not have cancer. The probability that you test negative is 205. But there's been some double counting here. We have to subtract out the probability that you both do not have cancer and test negative. Those would be the 200 out of 250. And so the total probability here is going to be 215 out of 250. This, I hope, makes some kind of sense, because amongst all those who do not have cancer or test negative, there are 215 in those groups. And so you should expect 215 out of the 250 who took the exam as the total probability. We also need to discuss something called conditional probability. The probability that event B will happen given that event A has happened. As an example, suppose that event A is that we have rolled an even number on a fair die. And event B is we have rolled a 2. What is the probability that we rolled a 2 given that we have rolled an even number? Well, there are only 3 even numbers on a die, 2, 4, and 6. So if we know that we have rolled an even number, the probability that we've rolled a 2 should be 1 in 3. A formula that works in all cases is the conditional probability of event B given event A is the probability of A and probability of B, probability of A and B divided by the probability of A. Let's see how that works out in this case. The probability of getting a 2 and an even number is same as the probability of getting a 2, which is 1 in 6. The probability of getting an even number is 1 in 2. When you divide fractions, you invert and multiply, cancel, cancel, yielding a probability of 1 in 3. As another example, we'll consider a fair deck of cards. Let's see, I'll take the jokers out, so the jokers are not part of this. There's another joker. Now, these cards have various symbols on them. One symbol is the club, which looks like a 3-leaf clover. Let's see, besides the club, there are spades. Which looks like, oops, a little point on the top. And then there are hearts and diamonds. Like this. These are red and these are black. The clubs and the spades are black. The hearts and the diamonds are red. These are called suits. Each suit has 13 cards for a total of 52 cards in the deck if you take the jokers out. The different cards are the ace, which is a 1, 2, 3, all the way through 10. That's 10 cards. A jack, a queen, and a king. So that makes 13 cards in each suit. We could ask, what's the probability of getting a queen given that the card I drew was red? There are 2 queens that are red, and there are 26 cards that are red, and so the answer should be 1 in 13. But we can calculate it using our formula as well. What's the probability of getting a queen and red, a red queen, versus the probability of getting a red? The probability of getting a red queen is 2 out of 52. There are 2 red queens out of 52 cards. But the probability of getting a red is 1 in 2. There are just as many red cards as there are black cards. So if we invert and multiply, four goes into 52 13 times, and so we get 1 out of 13. With our previous example, we had no cancer versus cancer. We had test negative versus test positive. We had 200 in the first group who tested negative and had no cancer, 5 who tested negative who actually had cancer, 10 who tested positive but had no cancer, and 35 who tested positive and actually had cancer. Let's find the conditional probability that you actually have cancer given that you test positive. There are only 45 individuals in the group who tested positive. So the probability, the conditional probability that you actually have cancer, 35, out of the total number who tested positive, 45, should give you that conditional probability. But we can test this the other way. What's the probability of both testing positive and having cancer? Well, to test positive and have cancer is, we need to calculate the probability that you have cancer and you test positive, divided by the probability that you test positive. The probability that you both have cancer and test positive would give you 35 out of 250. But the probability that you test positive is 45 out of 250. When you reduce the fraction, you end up with 35 out of 45. So we've introduced a couple new formulas that you need to remember. First, the additional rule. The probability of event A or B is the probability of A plus the probability of B minus the probability of A and B, which subtracts out the double counting. The probability of event B given event A, this is the conditional probability of event B given event A, is the probability of A and B divided by the probability of A. I thought that I'd show you a little example with my deck of cards here. I'd start off by shuffling the deck, and then I'll cut the deck like that. Okay, so I've shuffled and cut the deck. Now I'm going to rifle through the deck and pull out from the middle of the deck a card. In particular, I'm going to pull out the Ace of Spades. Okay, so that's one card. Now, we need to shuffle the deck again and cut the deck again. And I'll pull out from the middle of the deck yet another card. And in particular, I'll pull out the Ace of Hearts. So let's try that again. Let's take the deck, shuffle it, and cut the deck. We shuffled and cut. Now from somewhere in the middle of the deck, I could even close my eyes while I do this, we find the Ace of Diamonds. Okay. I suppose that we could only do this one more time. And so, somewhere in the middle of the deck, we have the last card, and that should be the Ace of Clubs. And there it is. So I ask you, what is the probability of me pulling all 4 aces at random? Just some random process without cheating. What's the odds? What are the complementary question is, what are the odds that I'm cheating? So we can calculate these things. What's the probability of getting 4 aces? This is the probability that I first draw is an ace, and the probability that the second draw is an ace, and the third draw is an ace, and the fourth draw is an ace. So we have a bunch of and statements here. Each of these, though, has a little slightly different possibility. If I have 52 cards in the deck, the probability that the first card that I draw is an ace is 4 out of 52. But the second draw has only 3 aces left in the deck and 51 cards. So the probability that I have an ace on the second draw is 3 out of 51. For the third ace, there's only 2 aces left. So 2 out of 50 cards that are left in the deck. And for the fourth draw, that's 1 out of 49. So what does that add up to? We'll hold out our trusty calculator and do 4 times 3 times 2 times 1. That's 24. So the numerator is 24. And in the denominator, we have 52 times 51 times 50 times 49, which is 6,497,400. However, this fraction does reduce. How many times does 24 go into that? We end up with 1 out of 270,725. So if I did this without cheating, the probability of getting all 4 aces at once, one after the other, would be 1 out of 270,725. Obviously, I'm cheating. Another example is the flipping of a coin. How many times can I expect to get heads in a row? There's 1 heads, 1 time. Heads on the second flip. Heads on the third flip. Heads on the fourth flip. Heads on the fifth flip. Heads on the sixth flip. the 7th flip, the 8th flip, well, let's call that not a flip, the 9th flip, and 10 flips, all heads in a row. What are the odds of that happening? By the way, I should tell you, it's 100% since this is a two-headed coin. So I'm cheating again. Getting a heads and a heads, these are independent events normally. So getting a heads and a heads for independent events would be the probability of getting a heads times the probability of getting a heads. Normally, the probability of getting a heads is 1 out of 2 possibilities. So the probability of getting 2 heads in a row would be 1 in 4. The probability of getting heads and heads and heads would be, for independent events, 1 in 8. You can see then that for getting 10 heads, the probability would be 1/2 to the power of 10, or about 1 in every 1,024. Not a very likely event. This would be unlikely. So obviously, I was cheating because this coin has 2 heads. Here I have a 10-sided die inside of a 10-sided die. So when I roll it, you can see here I have both a 4 and an 8. I guess you could say that's 48. And 0 and 2 inside this time. There's a 2 in there somewhere. So that would be a 2. A 1 and a 0 this time, that's 10. How many different conceivable outcomes are there? Well, what happens to the inner die and what happens to the outer die we'll assume are independent events. And so you can see then there are 10 things that can happen with the inner die because it has 10 sides, and 10 outcomes for the outer die because it has 10 sides. So there are 100 possible outcomes for this particular die. Here you can see I rolled an 87. This is a 20-sided die. Let's suppose I roll that together with my 12-sided die. How many outcomes are there? Well, there's 20 outcomes for the 20-sided die and 12 outcomes for the 12-sided die. And so there's 20 times 12, or 240 possible outcomes for each roll.